So lesson 5 is introducing graphs of quadratics. It's titled Key Features from Graphs of Quadratics. And the section 5.1 workbook is all about domain, range, and intercepts of quadratics. So it's just really kind of breaking down all the specific details of these graphs. And before we get started, a quadratic is just anything that has basically like x squared as its highest power. So for example, it would be like, say we have f of x equals just x squared, like that would be considered our parent function. Or you've seen like kind of standard form of a quadratic, which is ax squared plus bx plus c, but a quadratic is something, any like function that has x squared at least. There can't be any higher powers of x, like there can be an x to the third power, but there does have to be that x squared there. If it's not there, then it's no longer a quadratic. And then the graph is that kind of like U-shaped parabola that can open up or open down. It wouldn't ever like open sideways though or anything like that. Okay, so starting with 5.1. So up at the top, domain, range, and intercepts of quadratics. So the domain is the set of all possible input values for a function, which all the input values are usually our x values. Something that like you would take and plug into the function itself to find output values, which output values are the range. So a set of all possible output values, which is usually our y. And then just a reminder, when you're graphing, the like horizontal axis is the x-axis, the vertical axis is the y-axis. So on the right, there's this function graphed f of x equals x squared minus 2x minus 8. And then we just want to write the domain and range for that function. So we're going to write domain and range in what's called interval notation. And interval notation uses parentheses and brackets to describe the domain and range. So brackets are like the straight parentheses, for lack of better terms, and then parentheses, of course, are curved. We'll talk about what they kind of mean and when you would use each one in a second. So domain is all the possible x values. So when you're looking at a graph, it's basically like how far does the graph extend to the left and how far does the graph extend to the right. And with this graph, you can see like it kind of starts going vertical, but it'll never be like entirely straight up and down because that would mean it's no longer a function. Same thing over here, like it's gonna continuously go like, even though it's at a slow rate, it's gonna keep going like up and to the right, and then over here we'll keep going up and to the left. It's never gonna stop. So what that means is that for our domain, it's every possible x value because it's going left and right forever. So we would write that as it's between negative infinity, which is like the smallest possible x values, and positive infinity, which is the largest possible x values. It's basically going in both directions forever, like left and right. And then we're deciding between whether to use brackets or parentheses. So brackets mean that it includes that value. And then parentheses would mean it's like up to the value, but does not include. And that'll make more sense once we go over range. So since infinity is not like technically a number, we can't like include infinities. So anytime you have infinity, you would have a parentheses around it and not a bracket. Okay, so domain is between negative infinity and positive infinity. That just basically means like any possible x value is good. And then for range, the range is all the possible output values, so y values. So if we look at our graph, we can see it's like definitely going up forever and ever and ever. It's going up like pretty quickly too, but it's not going down forever. Like there's a definite low point on this graph. It's called the vertex. And we just kind of want to identify what that point is. So it looks like 1, -9. So remember, you go like right 1, and then we have to go down 9 to get to that point. So 1, -9. And then that's like kind of like our low point of our graph. So that's the lowest possible value for our range or for our y values that we'll have. And then we just kind of like go up from there. So since we're talking about like the output values, the y's, the like height of the graph, we're solely focused on the y value of the vertex, not the x coordinate. So that -9, that's the lowest point on our graph. So when we write our range, -9 is going to be the smallest value that we could have. And then we know like it's going to go up forever and ever and ever. We can see that on the graph. So it's going to go up to positive infinity. And then when we're deciding between brackets and parentheses, we have a point exactly on -9. So it includes -9 in the range. So we would put a bracket around -9. And then again, we can't really like include infinity. It's not like an actual number. So we'd put a parentheses around there. So you can have like two brackets, two parentheses, or a mixed match. It just kind of depends on if your graph actually includes that value. And then just remember that you can never like include infinity or negative infinity because it's not like an actual number. Okay, and then moving down to, I'm gonna add a note actually before we move down, but just that the name of like the way that we wrote domain and range is called interval notation. So if you ever like wanted to look up extra examples or anything like that, that's what you would look it up by. So interval notation. So x-intercepts, moving down here, it refers to the points where the function crosses the x-axis. They also help determine like the zeros and the factors of the function. So zeros just basically mean like the x value that make the function equal 0. So we find them, like we know what x-intercepts are. They're where they cross the x-axis. So we cross at -2, and then we cross at 4. It's not really over the 4, sorry. We cross at 4. So those are zeros. They're also like solutions, like if we had an equation form of this function. So if I like popped a 0 in here and solve that equation, I would get -2 and +4 as my solutions. So down in here in the description, it says they help determine the zeros, which they just are the zeros, and the factors of the function. So they can kind of help us if we didn't have this function, if we need to write one for this graph, we could get that from the x-intercepts. So like zeros are solutions, all those kind of like things meshed together. They're all kind of like very, very similar. So if I say their solutions, okay, I have a 0 at -2 or an x-intercept at -2. So I'm going to say x is equal to -2. And then I have another one at 4. So I'm going to say, okay, x is equal to 4. And then so now they're kind of in like solution form. So if I wanted to think backwards to like, say when we're solving by factoring, we set each factor equal to 0. I'm going to work backwards like in that process. So right now I have the solution. I want to get this equation equal to 0. So I'm going to add over the 2 because I want to cancel everything out on one side. So it's just a 0 there. So then I would have x plus 2 equals -2 plus 2 is 0. I'm going to do the same thing over here. So I'm going to subtract over the 4. And then I have x minus 4 equals 0. And then now I'm kind of at the point where I would have just taken like my two factors and set them equal to 0 to solve. So if I'm working backwards, the next step would be to bring my like two factors together. So one would be x plus 2, one would be x minus 4. So x plus 2 times x minus 4. And then say my problem wanted my function or equation to be in standard form, I would FOIL it. So like we're kind of multiply the equation together. I'm just going to pop this equation off to the side so I have a little bit more room. So if I FOIL, the x times x, so x squared, x times -4, so -4x, 2 times x, so plus 2x, and then 2 times -4 is -8 equals 0. And then I can combine like terms. I can combine the -2x, or sorry, the -4x and then 2x. So then I have x squared. -4x plus 2x is -2x minus 8 equals 0. And then now I just kind of created like the exact, I know we have the equation up here, but this would be a way that you could write the function if you weren't given it. So notice it's the same thing, like x squared minus 2x minus 8. I know one has 0, one has f of x, but those are like the like kind of cousins of each other. One is in function form and one is in equation form. So it's kind of cool that you could just take the x-intercepts and write a whole function from them if you weren't given the original function. Okay, so main thing from this section is just recognizing that x-intercepts, zeros, solutions, factors, they're all kind of part of the same family and all kind of tell you the same amount of information. Okay, so this next little table is a good thing to have in your notes. It just kind of breaks down like these few key features. So x-intercept, a point where the function intersects the x-axis or crosses the x-axis, and it just looks like a point. It's an ordered pair. And then a zero, it's the x value for which y equals 0. It just basically is like what x value makes the equation equal 0. So if you were given like a function and you were asked to find the zeros, I know we've done this in a previous section, that's when you would like take 0 and pop it in for f of x to solve for x. So kind of related, or it is related to that. It's the same thing. And then the last one, a factor. This is pretty wordy, so if you want to paraphrase it, I totally get it. But a monomial or a binomial that is multiplied together with another monomial or binomial to get the rule for a function, and it can be found by using the zeros. So that's exactly what we did like in this whole section. So we took the zeros, which were x equals -2 and x equals 4, and then we found the factors that created those, which were x plus 2 and x minus 4. And then we took those and we multiplied them together. So that's where like it says we're multiplying them together. Sorry, that's not supposed to be crossed off, but we just kind of did that whole process there, kind of working backwards. And instead of like solving an equation, working backwards to write the equation itself from the solutions or the zeros. Okay, so you can paraphrase it however you want. I definitely think that like this example with the graph is important to have in your notes though. Okay, so the next section, positive and negative intervals. So positive and negative intervals describe like where the function is above or below the x-axis. So if I look at this graph, I can cut it in half by the x-axis. So and I can cut it in half by the y-axis too, but we don't really care that much about that. So if I cut it in half by the x-axis, there's like this top half, and then there's this bottom half, and we're gonna describe each of those. So for describe where the function is positive, it's where all the y values are positive, so it's the top half of the function. It's like all of these points anywhere along the line right here or the function right there, those all have positive y values because they're all above the x-axis. So if we want to describe that, I'm going to erase some of this. If we want to describe that, we need to describe this portion of the graph and then this portion of the graph. And unfortunately, we can't describe it like kind of all in one piece because there are two separate pieces even on the graph. But we do need to kind of consider where they cross into no longer being positive, and that's on the x-intercepts. So at -2, just gonna write a little bit bigger, it's kind of hard to see, and at 4, that's when it goes from either being positive to being negative or being negative up to being positive. So we'll just have to write it in two different ways. And we're still gonna write it in interval notation. So I'm gonna do this portion first. So I want to write or describe that in interval notation. So this portion, and when we describe it in interval notation, I'm going to kind of backtrack a little bit. So we always kind of follow the graph like from left to right. So we're going this way, and then we're going this way. So if we're describing the graph like from left to right, we're going to describe the x values for which it's above the x-axis and then or below it if we're talking about negative. So this whole, the like highlighted green portion, it's kind of ends being positive right here at that x-intercept because that's when it goes below. But it like continuously is positive anywhere beyond that. So anything to like the left of that point, it's always, I'm gonna kind of draw it this way so it's a little bit more clear. Anything to the left of that point, it's always gonna be positive. It's not gonna bend back down and turn around. So we can describe that as between -infinity and -2. And then around the negative infinity, we need the parentheses because we can't include the like infinity in it. And then it's kind of tricky when we're deciding between the bracket or the parentheses for the -2. So at -2, it's technically -2, 0 is the point. So at that point, it's neither positive nor negative, it's 0. So we wouldn't be able to include -2 either. So we would put a parentheses around there. So that interval describes the part of the graph that's highlighted in green. So it's like the x values from negative x equals negative infinity to x equals -2. It's always going to be above the x-axis. And then we still have to describe this portion over here as well. So this is the point 4, 0. So if we're describing that, it kind of starts like when it first becomes positive again. So like it's like negative, 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 positive. It starts at 4. And then it's going to continuously like be positive. It's not going to like turn back around. So from 4 to positive infinity now, oops, from 4 to positive infinity is when the graph is positive as well. So between the, or like those two separate intervals, the graph is above the x-axis and it's positive. And then same thing here when we're deciding on brackets. Of course, like it's a parentheses around the infinity because we can't technically include infinity. And then at 4, the like graph is neither positive nor negative, it's equal to 0. So we wouldn't put brackets around 4 either because it doesn't include 4. At 4, it's exactly 0, it's not positive. And then now we have to do the section that's negative, which is the entire section that's below the x-axis. So that's this portion. And because that part is connected, it's not in like two separate pieces like our positives were, we do just get to do one bracket there. So I'm going to kind of color code this a little bit better. We'll say the negative is going to be in blue, and then I'll keep the positives in green. So for the negative section, you can see if we follow the graph from left to right, going down, 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 and then it crosses into a negative at this x-intercept -2. So it's going to be the start of our interval. And then it's going around, it goes to the bottom, and then it crosses back up into the positive section at our other x-intercept 4. So our like end of our interval would be 4. And then remember, neither of our intervals are going to like include -2 or 4 because it's not positive or negative at those points. The function is equal to 0, and that doesn't fall into either of those categories. So we'd put parentheses around each of these. So the big kind of, I guess, objective from these types of problems is just recognizing that when you're going from like a positive to a negative section on the graph, the barrier or like the cutoff is the x-intercepts. And it always will be because that's where you need to cross from like below the x-axis to above the x-axis. So 5.2 is about maximum, minimums, end behavior. It actually starts off with end behavior. So up at the top, this is kind of like, so what I have highlighted right here, that's kind of like your template for end behavior. So it's always going to look the same, and we're just going to basically fill in the blank at the end depending on what the graph actually looks like. And end behavior is just asking, what does the graph do on its left side? Does it go up or down? And then what does the graph do on its right side? Does it go up or down? So I'm going to kind of translate each of these because they're a little bit funky the first time you see it. So starting on the left right here, as x approaches negative infinity, that just means like as the x values are getting smaller. So what that means is basically as the graph goes left. Because if we're smaller and smaller and smaller, so they're approaching negative infinity. And over here, so it says as x approaches positive infinity, that just means as the graph is going to the right, that just means as all the x values are getting larger, because on the right side of the graph, all the x values are getting larger and larger and larger, so that just means as the graph goes right. And then in the blank, we're either going to fill in the blank like at the end with either positive or negative infinity, just depending if the graph goes up or finishes down. So I'm going to center that a little bit more. Actually, I might rewrite it a little bit. Sorry if you had to erase it, but we'll do positive infinity if it finishes up, and then negative infinity if it finishes down. And that should make a little bit more sense like after we kind of go through the examples. So, oops, that's not how you spell down, sorry. So the second part of the end behavior where it says f of x approaches, remember f of x and y are essentially the same thing. So it's kind of saying as x approaches negative infinity, so as the graph goes left, is it finishing up or down? Because f of x or y tells you the up or down on the graph. And then same thing over here, f of x approaches, that's telling you just if it goes up or down. So we're going to fill in these blanks with either positive infinity for up or negative infinity for down. It just varies by the problem. So we're going to answer the end behavior for these two graphs. And then like I said, like I already have this stuff written out because that doesn't change. So like you could start the problem with that every single way, and you should start the problem with that or that way every single time, I guess. Sorry, is what I meant to say. Okay, so I'm just going to focus on this graph on the left side first. So as x approaches I'm reading right here. As x approaches negative infinity, remember that just means as the graph goes to the left, what does f of x do? So f of x approaches. So on the left side of this graph, the left side of this graph finishes going upward. So that means that f of x would approach positive infinity, because that means the y values or the f of x values, the output, is getting higher, is going up to like higher and higher numbers, so it's going to positive infinity. And if you want, you can write like a plus in front of it, or you can just write it as just regular infinity because it's kind of assumed. And then now here with the second line, it says as x approaches infinity, so that means as the graph goes to the right, what is f of x doing? So as our graph goes to the right, it's going upward on that side also. So f of x is also approaching positive infinity there. And then every single quadratic graph or parabola has a like maximum or a minimum. They can't have both, but they can have one, or they will have one or the other. So it just kind of depends. It's always going to be what the vertex is. So if you look, our vertex is right here. And you have to ask yourself, like, is the vertex the lowest point on the graph or is it the highest point on the graph? And that's going to dictate whether it's the maximum or the minimum. So this vertex is the lowest. It's like the very bottom of the graph. So it's a minimum. So we can say there's a minimum. And then the point or like the value of the minimum, we don't really write it as like the entire vertex. So like this vertex is 3, -2, but we're just talking about the height here. So we're just focused on the y coordinate. So we would say a minimum at -2 because that's the height of the point. And minimum is just whether it's the highest or lowest point on the graph. Okay, so moving on to like this side now. So from right here, as x approaches negative infinity, that means as the graph goes left, g of x, and the name of the function just changes now, g of x instead, but it's the same idea. So g of x approaches. So as the graph goes left, as this graph goes left, it finishes downward. It goes down and left. So that would mean that g of x approaches negative infinity because it goes down. So positive infinity is up, negative infinity is going to be down. And then on the next line, oops, I didn't mean to erase that. On the next line, so this was left, and then on the next line, x, or as x approaches positive infinity, that just means the x values are getting bigger, so the graph is going to the right. So on the right side of this graph, it's finishing going down on that side also, so g of x approaches negative infinity. So remember, negative infinity means down. And you'll notice that like both end behaviors, they kind of ended up with like the same answer. So it's either up and up or down and down. That's always the case for quadratics because they're like that U shape, so they'll always finish going in the same direction, but that'll kind of change depending on the different types of functions that we're studying. And then for minimum or maximum, right here, so we're looking at kind of the point where the graph changes direction, the vertex, which over here, it's the point -2, 3. And then we have to ask ourselves, is that the highest point in the graph or the lowest point in the graph? And in this case, it's the highest point. So it's a maximum. So we would say there's a maximum. You could just say max if you want. And then over here, you could just say like min just to shorten it. But max at whatever the height of that point is. So the height is always the y value. So we would say there's a max at 3 because that's like the highest possible value on that graph is at 3. You'll see there's no like random points that are anywhere above it. And then moving down to increasing and decreasing, these are the same graphs, but you'll kind of see like I write a lot on the graph, so I didn't want it to get like too cluttered. So increasing and decreasing intervals. So this is, we kind of have to treat like reading graphs, like reading a book, like you would read left to right, and we do the same thing here. So we're just going to start on the graph on the left. I'm just going to go ahead and zoom in. So describe where the function is increasing, and then describe where the function is decreasing. So before we get into this, I can see like this graph, we would consider it increasing like as a whole because it's opening up. And then like this graph is decreasing as a whole because it's opening down. But there's portions of the graph that are increasing and portions of the graph that are decreasing once we break it down. And to figure those out, that's when we have to kind of follow the graph from left to right. So if I follow the graph from left to right, it starts off going downward and then it hits the vertex. So 3, -2. And then after it hits that point, it goes upward. So since we're following the graph from left to right, the point that kind of dictates left to right is the x-coordinate. So now we're focused on the x-coordinate of the vertex as opposed to the y like we were with the minimum and maximum because we're going left to right instead of up or down. So if we would want to describe where the function is increasing, that's when it's going up. So it's increasing over here. So the point where it starts increasing is at the x-coordinate of the vertex, which is 3. And then it continuously increases. It doesn't like turn back around or anything. So if it's continuously increasing after that, it would be increasing through infinity. So forever after that. And then when we're thinking brackets versus parentheses, so at the vertex, it's neither increasing nor decreasing, it's just kind of neutral. So we'd have to put a parentheses around the 3 and then always a parentheses around infinity. And then now for decreasing. So if we're reading it from left to right, it starts off going downward, it's decreasing over here. So the point where it stops decreasing, if we're following it from left to right, that's the vertex. That's actually where our interval is going to end at that 3. And then it's decreasing everywhere to the left of that point. So like all the x values that are smaller, so it'd be -infinity. And then parentheses or brackets, always parentheses around -infinity or around infinity in general. And then remember that vertex, the point like at x equals 3, it's completely neutral. It's not increasing or decreasing, so we can't include it. So we'd use a parentheses. Okay, this would be a really good time to like pause and test yourself and see if you could do this next example on your own and then just play the video to check your answers. Play it once you're ready, but for g of x, if we follow the graph from left to right, we start off going upward, then we hit the vertex at -2, 3. Then after that point, we're going downward. So since we're following the graph like from left to right, our focus is on the x-coordinate of the vertex. So now kind of our like boundary line. is at x equals -2. So for where the function is increasing, we were increasing on the left side of the vertex. So that's from, that basically means like we're going to stop increasing when we get to the vertex. So that -2 from the vertex is going to be the end of our interval. So -2 is going to be the end of our interval. And then everything to the left side, so every single smaller x value is going to be where we're increasing. So -infinity would be the start. Not really like a start, but we'll be increasing from -infinity to -2, which just basically means anything to the left of -2, of x equals -2, which is this line right here. And then parentheses around -infinity. And then same thing here, the vertex is kind of neutral. It's where it shifts from increasing to decreasing, but it's neither of them specifically. So we put a parentheses around -2. And then for where is the function decreasing, once we hit the vertex, it shifts downward, it starts going down or decreasing. So it's starting to decrease at the vertex, so it's starting at -2, and then it's continuously decreasing like anywhere to the right of the vertex. So it'd be to -infinity. So that just basically means like from x equals -2 and any like x values to the right of it, because that's where all the x values are getting larger. And then vertex is neither increasing nor decreasing, it's neutral, so parentheses around -2, and then always a parentheses around infinity.